Hello and welcome to this tutorial. This is a very interesting topic. Today we are going to work on making music with recurrent neural network, machine learning, AI. This is a lab that belongs to MIT's deep learning uh, lecture series. You can watch their lecture series on YouTube. It is very awesome, it's very interesting, and uh, each video lecture on YouTube has a corresponding lab on GitHub. You should run it on Google Colab. You can run the chunks of code. You can run them live in here. You don't need to download or install anything. So the thing we are going to do in this video is we are going to generate a neural network model to make music, make beautiful music. We will feed it some data, some songs, and it will, at the end, it will make its own music. It's a very interesting subject, and it's very very well explained in this lab. So the first thing we are going to do is we are going to import dependencies. So TensorFlow, obviously, then MIT Deep Learning as MDL. This is a library that belongs to this lecture series. You don't need to know anything about this since it's not so related to deep learning libraries and all. NumPy to work with arrays and numbers. OS, we're going to import, we're going to open files and work with directories. Time, very obvious. Functools, IPython, TQDim, DM. These are not so much related to machine learning and deep learning. So we run this to import the libraries. The next thing we need to do is we are going to import our dataset. Look at our dataset. So as I explained before, that our dataset is a set of songs, but these songs are not in the form of audio files because we can't work with audio files are not as they are suitable for machine learning. So what we do here is songs are in the format of ABC notation. Okay, ABC notation. The songs are in this format. You can see here the songs are each song. So each song is an array of strings. For example, you can play one of them. It takes a while because this library changed that notation into an audio waveform file. You can have a look at it. You can play it. It's a song, one of those songs that we have. One of those 817 songs that we have in our dataset. So the next thing we are going to do is we are going to join all of the songs and make a single variable as songs joined, and then we here sorted set songs underscore joined. What set does here is it removes all the for example, if you have 10 A's, okay, 10 A's, it removes 9 A's and it just keeps 1 A. Okay, so we don't have repetition of characters. And then we'll sort it, and at the end we have 83 unique characters in our dataset. So as you know, we cannot program strings, we cannot feed strings into our machine learning network. We need numbers, okay, because models work with numbers, matrices, vectors, and so on. So we have to relate each string in each character in our string to a number. Okay, so what we do here is we sort them here. You saw that we sorted those characters, and each number. Okay, so the index of each character in that sorted list will be the corresponding number that we relate that character to. So, for example, if in this array vocab, if A, for example, is the first character, its corresponding number will be 0. So here we do the same thing, and also we define another thing to bring back the numbers to the characters. We can see an example of it here. You can see n is 0, space is 1, exclamation mark is 2, and so on and so forth. So we have successfully vectorized our characters. So each character will relate to a number. So in these labs we have parts that we need to do ourselves. So here we have these to-do parts that we need to fill ourselves. So it has explained the write a function to convert the all song string to a vectorized representation. So in this function we will be given a string, and we need to turn it, convert it to a vectorized or numerical representation. So we write here return. So it should also be an np.array, np.array of, so the list is idx char to idx that we have defined above of s for s in string. So that's it. We convert each character in this string into an index. So we run this. Also, in the last line we feed the songs underscore joint variable into this function. So all the songs now are vectorized. We can here see an example of what our function does. So these 10 characters are mapped into an integer like this. So these are representation of this part of our data set. Now we need to make our training examples and targets. So in RNN, if you have watched the video lecture, in RNN we have inputs, okay, and outputs. So for training, input and output are the same, except the output is just one step further. Okay, so it has explained here that if our dataset is hello, therefore our input will be hell and our target will be lo. Okay, so these are our training input and our expected output or our target. So here we have vectorized sign, sequence length, and backslash Let me give you a quick explanation of sequence length or batch size, because they get mistaken easily. Sequence length, okay, so for training of our data, assume that we need five mm, five uh, chunks of data from our dataset. Okay, so that will be our dataset, our batch size. Okay, so 5 will be our batch size, and length of each chunk will be, for example, if it's 10, so we need 5 subset with the length of 10. There will be 10 will be our sequence length. Okay, so here we are going to use sequence length and batch size. So n is the length of vectorized song string. Index is np.random.choice n minus sequence length, and batch size, you can see we choose randomly. Batch size, for example, if batch is 5 or 4, if batch size is 4, we choose randomly 4 numbers between these in this range, 0 to this n minus sequence length. So that's our batch size. Now we have to define the input batch. Okay, input batch will be a list of input data. Okay, so using these indices, okay, we need to define our input batch. So input batch will start, okay, each input batch will start with this number, one of these numbers, okay, in this array IDX, and will start in that index and will continue in this amount, sequence length. Okay, so each input batch will have that length. So we have an vectorized from vectorized underscore signs from IDX to IDX plus sequence underscore length. Okay, sequence length, and obviously we're going to do this for if we have to I plus underscore for I in IDX. So that's it. We're going to do this for all the numbers in IDX. And this is our input, and output batch, as I explained before, is just one step ahead of our input batch. So we write the same thing, vectorized songs I plus 1 to I plus sequence length plus 1 for I in IDX. Okay, and the next thing we're going to do, this chunk of code will test our function to see if we have written it right or wrong. So we pass all the tests here. Also, we can have a look at our input and output batches here. For example, if our input is 26, it is expected to have 1 as output. If it's 1, it is expected to have 58 as output. So one thing that you have to keep in mind in recurrent neural network, we don't have just one step in training. Okay, our model will keep in his mind, in his history, the previous steps as well. Okay, so because in music, in song, you know that the songs are not written step by step. It's a sequence of notes of voices, of sounds, and then with respects to all of that sequence, the next sound will come. So Arn is very suitable for this kind of uh, music generation. Now we get to the part that we make our recurrent neural network. So our recurrent neural network consists of an embedding layer, an LSTM layer, and a dense layer. So embedding will make our inputs ready for the LSTM layer, and the dense layer will have our outputs as we expect, one of those 83 unique characters that we expected. So here we define our LSTM as we use keras.layers.lstm, and here we need to build our sequential layer model. So we use keras.sequential. The first one, as I said before, is layers.embedding. The second one is LSTM, which takes RNN underscore units, and then at the end we are going to use tf.keras.layers dot dense, and we are going to, and here we are vocab size will be the length, the size of this layer. You can see the units of this layer. We will have the amount of vocab size, the unique characters that we have in our data set. We run this. Okay, we tested. Model.summary gives us a summary of our layer, embedding LSTM dense, number of parameters we have. Here, check the dimensionality. X and Y, we use the get batch function. Predicted items model works on X and gives us predicted. You can see the shapes of input and prediction shape. Here we test our untrained network. Okay, so we're using the result of this part, the result of the predicted characters will be like this. If the input is this, the predicted is like this. You can see the untrained model does not so good on making music. So we need to train our model. In training neural network models, it's very important to have a sense of accuracy. Okay, how accurate our model is in each step. Okay, how accurate our model is in each training step. So we should know how accurate it is to take the next step. Okay, so this is very important to have that. We define a loss function here. We use cross API to compute the loss. Here you can see y true and y predicted. So, or labels and logits. So labels are of course y true. So we write labels, and also we write logits. It's our model. Batch loss, compute loss. For our model, for our untrained model, here we should write for our untrained model, we should write to compute using the next character from the example batch. Example batch is here. Okay, this is our example batch, x and y. So it will be y and predicted. Y and predicted. We run this and see how much our loss is. We can see that our loss is pretty big. So in this part we will define the parameters needed for training the model, training iteration, the number of them, batch size, sequence length, learning rate, vocab size, embedding dimension, RNN units. Also these are the files that the path that we are going to save the weights. Each step our model will result in a specific weight. Weights are very important, and it will save the weights in these directories. So model in this part, we are going to build our model, define the optimizer, and define the function for each training step. So the model, okay, here as we defined above, takes vocab size, embedding dimension, batch size. So I just copy these. I'm not sure if copy that. No, didn't. So let's write them. So just vocab size, vocab underscore size. If you remember, we have defined all of these here. Okay, we have them here. The next thing is embedding dimension, underscore dimension. The next thing is RNN units, and the last one is batch size. So this is our model. It has advised us here to use Adam optimizer. So we from TensorFlow Keras API optimizers dot Adam. Okay, here we define the function for training step. So in training, I said that in training is very important to have a sense of accuracy, and we define the loss function. Here we after each loss, okay, we define the loss. The next step, okay, the gradient. How much, how far we are, how much is the speed of change with respect to the true value, okay, of the result of our model, the predicted amount from the true value is. So that is gradient. Very important. We use gradient tape from TensorFlow. Y hat is model that works on X input. Compute loss, the function that we defined above, labels and logits. So labels here are, of course, Y, and logits are Y underscore hat. And the next step, it wants to calculate, compute the gradient to take the next step. So gradient will take the loss, and with respect to all of the trainable variables, it will calculate the gradient. So that's it for our train step. We have defined that, and training begins here. This is the most important part. So history, we define history, plotter, these are for plotting. So you start iterating, okay? For the numbers we have defined above for training iterations, x batch, y batch, the function from vectorized sign, sequence length, batch size, the amount of loss, and we append this loss and plot it. If it's multiple, each 100 times we save the weights, and we continue the iteration until it's finished, and at the end also we will save the weights into the specified directory. Here save vocab size is not defined. Let's go above vocab size. Yeah, I forgot to run this part. Run this again. Another problem. Apply gradients in this part. That my mistake was that I didn't added learning rate in here for the optimizer. Now that I've added it, everything is supposed to work just fine. Let's run this chunk of code. Okay, after running this, it starts to train the model. So it trains the model, it plots the losses with respect to each iteration. I will pause the video because it's going to take some time, and we'll be back after the training is done. Okay, because the model was running so slow for me, because of I don't know, some time limiting on GPU on Colab, I limited the iterations from training iterations to 100. So it stopped at 100. So we can see at the iteration goes up, the number of iteration goes up, the loss decreases. Okay, the next thing, now we have trained our model, and our model is ready to generate some music. We need to change this model to batch size of 1, because we need the model to give us one character after another character to generate music. So we define the model again as we have done once. So vocab size, first one, the next one is embedding dimension, next one is RNN units, and batch size equal 1. We run this, and model.summary is this. Now we want to generate music. So as you can remember, music in this program is a text. Okay, it's a string. So we need to generate text and a string from the predicted numbers that we got from our model. So we need to define this function to do that for us. So it gets to the model, the start string, and generated length. So we got a string. Okay, we need to, as you can remember, we need to convert this string into numbers. So an array with defined at the beginning char to index s for s in string. This will be our input evaluation char to index. It will convert the characters in our string into indices. And here we are going to define the predictions. So predictions, the model works on input eval, of course, input underscore eval, squeeze predictions, tf.squeeze predictions, remove the badge dimension. Now here predicted id tf.random categorical predictions. Here we should write predictions. It receives the predictions, the lowercase p, and expand dimension. Here text underscore generation dot append, and here we should because we want to append to the text generated, we need a string, so we need to convert back the index to the character. So index to char of for I in char of predicted ID. Then return the start string plus space and join it with strings. Now we run our string, our generated text function. Here problem, name string is not defined. Start. Oh, sorry. I have to write start underscore screen. Let's run it again. Okay, now it's generating text related to our model, and we convert this text, this ABC notation, to waveform song files, audio files. So because you can see, because our model was not properly trained here, just 100 iterations, it didn't give us any songs back. Okay, I think at least you have to have 2,000 iterations in order to have to be able to generate some music. So because of the limitation, GPU limitation, processing limitation for me on Colab here, unfortunately I'm not able to do many more iterations, and you can try changing iterations, batch sizes, and other things in order learning rates and stuff like that to test and experiment and to see how these things affect the song that is created by your model. So that's it. The lab is over. Thank you for watching. Hopefully I will do another of these videos for other labs of these lecture series, and do these explanations and solutions on those. So again, thanks for watching, and see you again on my channel. Goodbye.